Welcome back everyone. Part 2, changing matter. I mentioned this briefly in the first tutorial. Now we're going to explore it further. Just to recap, we've been talking about solids, liquids and gases, what their properties are and how they are formed and how they work. What we're going to look at now and move on to is how to change those states of matter. What we have to do to them to get them to become something different. Okay, to get matter to become something different, we need to go to extremes. Maybe have a think, have a chat to the person who's close to you, it might be your dog, it might be a family member, about what you think, what kind of extremes you think we will need to change matter. Okay, if you came up with some ideas like we might have to change their shape or maybe their colour, then you're on the right track. We actually need extremes, extreme temperature and extreme pressure to be able to change our matter. We're going to focus on a natural element today of water. Water is H2O, so that's, in chemical speak, that's hydrogen, 2 oxygen. Again, having a look at the diagram on the board behind me and you'll be able to see, if we zoomed in, we can see those particles and atoms nice and close. 70% of our world is covered in water, guys, but only 2.5% of that water is fresh, drinkable, usable water for human consumption. So conserve that water, people. We're going to have a look at how water changes states of matter today. It's a very flexible element, which is why I'm using it, and it's easy to gain access to. You can see here that I still have my orange water that I made earlier from our previous experiments. I'm just going to recycle that one so that I'm not wasting my precious water. So we know that in this state, our water is a liquid. And in my beaker here, I have 250 mils of water, which is 1 cup of water. So we're going to play with this 1 cup of water. And the measurement is a little bit important for us to be able to do our experimenting with today. Now that we, like atoms and molecules, have bonded with our water in its liquid form, we're going to have a look at how to change that state of matter. We just said we need extreme temperatures or pressures. We can't formulate those pressures, but as that's generally a natural occurrence, but we can create an extreme temperature change. If I wanted to turn this liquid, my orange water, into a solid, how do you think I would do that? What have we got at home in our environment that will help us turn this nice liquid into a nice solid? And will it be the same? What differences will we see? Hopefully you guys answered those questions and you were able to tell me why it's not fitting into the container, why I can't compress it, why or what is happening to those particles in our solid form compared to our liquid form. So, if you decided that you would need to freeze or cool down your water to turn it into a solid, you would be 100% correct. Does anybody know what temperature water freezes at? I do. It's 0 degrees, which makes it really, really super cold. If you were to check out the settings on your fridge or your freezer, ask mum and dad or whoever's at home maybe to help you with that. It should tell you that your freezer is set to 0 degrees or colder. You might see a little -2 or -4 depending on how your fridge works in your family's settings. So, earlier or previously I have created a solid from my liquid. Now it will look a little different. I didn't colour it, so it just looks like normal water, normal coloured water, clear. Okay, so I said I had 250 mils of water in this cup. Well, I measured out 250 mils of water and I froze it. I changed its state of matter. I cooled those particles and atoms down so much that they stopped moving, because that's what happens to those things when we extreme cool. everything slows down and stops working, which is why sometimes you might feel yourself getting a bit tired if you're in the aircon for too long. I have my fishbowl back. We're going to do a little bit of comparing now. So we still have the 250 mils of liquid in its first state. Now, clicked my fingers and magic happened. I have ice. I worked out that there are 23 of my ice cubes will equal 1 cup of water. So here in my fishbowl, I have the same amount of liquid as I do in my beaker. I also have an empty beaker here because we're going to see the difference. We want to make a comparison. We've got some talking to do. In my fishbowl, we can already see a difference. You can see the shape is different. You can see where this one's taking the shape of its container, this one is not. It's the same amount of liquid, guys. We've just changed its state. We've solidified it. Turned it from liquid, free-flowing particles into our solid. Now, let's do our comparison. Will the same amount fit into this second beaker? What do you think? Why is my 250 mils of water not fitting into this container when it fits into this container? What's going on? Why does it look like that? Can you answer these questions for me? Okay, now that you've had to think about those questions, we're going to talk about why this is going on. Because we've created a solid. Okay, and we know that solids have regular patterns and fixed shapes and can't be compressed, squashed into that container. So I could make my hands really, really cold by trying to push down on this and force it in, but all that would happen is I would probably break my beaker. So until this ice melts, it is going to stay a solid. Oh, I just gave you an answer there. If I wanted to reverse the change or revert back to the original form, the original state of matter, what would I have to do to my ice? What would I have to do to my solid? That's right, melt it. I told you the answer. To return this to its original form, we would just have to melt it. Now, I can sit here and wait and let it melt, or I can do this. So here we have my solid in the saucepan. You can see the red underneath the saucepan, meaning that the hot plate is on and it's very hot. Reminder, please ask for assistance if you're going to do this. So we're going to start melting our ice, which is what the process is called when turning from a solid to a liquid, melting. It might take a little bit of time to get going, so you will need to have some patience with this experiment. If you can see, the bottom of the saucepan still looks quite cold. There's a little bit of mist happening on the outside. If you listen carefully, you can just start to hear the ice crack. You can see that the bottom of the saucepan is starting to heat up as the ice is starting to move and wiggle around. You may also be able to see some little bubbles start to form under the ice. That tells you it's heating quite rapidly. I have the oven on quite hot, or the stove on quite hot, to make this a speedier process. You can see now that a lot of the big pieces of ice have started to melt away. They're starting to move a lot more than they were before. When we see some more bubbles start to form on the bottom of the saucepan, that means it's getting hot, and we should see our third state of matter. So we can see our solid has now turned into a liquid. Carefully looking over the top of the saucepan, now I can see some bubbles. They're starting to move a lot faster. I wonder why they're moving faster. Now they're starting to disappear altogether. I'm starting to get slightly bigger bubbles that are moving a lot faster, and I can see a lot more steam. So I can see that gas, that water vapor. Wow, I was really excited by watching that ice melt. It was super fun. Okay, hopefully you've worked out now that to change the state of matter from a solid to a liquid, we have to melt it. That's right. Can you tell me, maybe do you think, what temperature ice starts to melt? I'll give you a hint. It's similar to the answer I gave you before about when water freezes. 0 degrees, that is correct. At 0 degrees, when we remove the ice from the extreme temperature, is when it starts to melt. Because as we take it out of that 0 degree, that controlled cold temperature, and bring it into the room temperature or to a hotter temperature like in our saucepan, we get instant melting. My cup has been sitting here, and my beaker has been sitting here for a little while now, and I'm starting to get that liquid forming back in the bottom of the glass. It's taking a lot longer though than my saucepan. To freeze and to change our liquid, we need to freeze it and into a cake. Let's look at our final change to state of matter. We saw with the saucepan that we actually created the third state after we melted it, and we kept adding heat, so we increased the extreme heating process after we'd melted our solid ice back into water. What happened to the water once we kept adding extreme heat is we saw this nice steam starting to rise out of the top of the saucepan. We could see that steam because it has water vapors in it, which makes it a little bit heavier than the air and the oxygen around us, which is why it rises so far and then disappears again, because it gets evaporated up. A fantastic way to watch the process of evaporation and condensation is to create your own water cycle at home using a bowl, a couple of rocks, a bit of Glad wrap and some water. Okay, let's have a look at how else we can watch states of matter change. Now, we didn't really see anything when I blew this balloon up. I just put my gas into the balloon and trapped it in there. So what we're going to look at now is I have some common household items that we've all used before. I have some vinegar in this bottle. I have some bicarb soda in this bottle. Now, we've all made the volcano. We've all watched the fantastic chemical explosion. We're not watching that chemical explosion today. What we would like to do is change this solid and this liquid into a gas by mixing them together and causing that chemical reaction. So I have here a funnel, which I put 2 spoonfuls of bicarb soda into a balloon using a funnel. If you don't have a funnel, just roll up a piece of paper, it will do the same trick. Be sure to wipe the lumps out of the bicarb soda so that it doesn't get stuck and you don't have a big mess to deal with. I have also just used an empty old bottle that was laying around the home as well. Okay, so what I'm going to do is, if my bicarb's in here and my vinegar's in here, I'm going to place the neck of the balloon over the bottle. You may need some help with this bit. And when I count down, I'm going to tip it upside down and put my bicarb soda in. Hopefully what we should see happen is the gas rising and inflating our balloon. Now, we can't see gas because often it is invisible and odorless. We will be able to see it though if our balloon blows up. Okay, here we go. Steady hands, it is a bit tricky. Right over the top of the bottle. Okay, are we ready to create and catch some gas? 3, 2, 1. That. We even managed to get some of that liquid into our balloon. We created that much gas. You can see the leftover stuff on the side. This is the stuff that hasn't dissolved, hasn't mixed in, or perhaps it's just residual from the gas, because with our steam, as we know, sometimes the gas can actually pick up extra particles and fling them around. Have you ever heard of it raining cats and dogs? Kind of the same theory. If you want an extra experiment to try at home to observe changes to states of matter, to observe how particles move and are affected by those changes, then I have a quick one for you. If you have a bouncy ball or a rubber handball, not so much a tennis ball, what you need to do is pop one in the freezer for about 40 minutes, put one in direct sunlight for 40 minutes, and then bounce them together at the same time. Or you could bounce them separately and measure how high they bounce back. This will show you that when we freeze or use extreme temperatures to cool down a liquid to make it a solid, that the particles slow down even further. Same with the heating, that you should discover that your ball will bounce higher once it's been heated up because those particles are moving faster. Happy experimenting! Tune in to part 3 in the next tutorial.